All right, we're right at the hour. Hi, everyone. Thanks for joining us in this webinar for Accurate Heat Exchanger Design. Keep in mind that this webinar is being recorded, and we will send the recording out to you following this webinar. If you have to leave early, if we miss it, we'll get a copy to you of this webinar. I'm joined today by my colleague, Yurika Diaz. She works in customer success. She's worked at ChemStations for a long time. Welcome, Yurika.
Hi, Noel. Hi, everybody. It's a pleasure to be here with you today. And so we're going to give you today, the webinar today is talking about using ChemCAD NXT for accurate heat exchanger design. So we're going to talk about our heat exchanger product, and let's go start our webinar. Okay, so let's go start. So the project or the objective for today is to illustrate how ChemCAD heat transfer program, CC-term, what we call CC-term, can be used to estimate or design a new heat exchanger or to rate an actual heat exchanger. And to demonstrate how CC-term uses the simulation flow sheet data and exchanger geometry to perform heat transfer calculations. So that's our main object, and we're going to use some cases to see how this is done. So the agenda will be to go through some heat exchanger types, what kind of types can be modeled, what kind of heat exchanger types can be modeled using CC-term, what kind of equations are used when the heat transfer calculations are performed, what kind of calculations can be done in CC-term, like what model. So we can design, as I mentioned before, we can rate an existing heat exchanger, and we can use in some Fulling rating or calculate Fulling factor or estimate Fulling factor calculations. We will go through some case studies, going from designing an exchanger based on a process that we are given, and go through how to optimize this heat exchanger and put it in practice into an existing process. And then finalize it with what we call a simulation mode, where we put the actual optimized heat exchanger through our process into our flow sheet to see it working through ChemCAD NXT. Okay, so that's our agenda for today. So let's get started. So what type of heat exchangers can we model with CC-term? So CC-term can be used to be model shell and tubes with heat exchangers, plate and frames, as you can see here, double pipe heat exchangers, and air coolers, whether they are forced draft or induced draft. Okay, but most of the popular that we have seen are the ones that I work the most or support works the most are shell and tubes. Okay, those are the most popular heat exchangers that we model. So CC-term actually follows different standards, but the most popular is TIMA standard. And TIMA class has TIMA class R, TIMA class C, and TIMA B class. Okay, but we also have ASME, so you can select the standards. DIN AD, British Standard 5500, and non-standard. So these standards actually follow certain criteria and defaults that you can use to model the heat exchanger. Most of the time, TIMA class standard is what we use or model most of the heat exchangers that we see. And as you can see, this is a different types. Most common that are used different for the head of the heat exchanger, the body of the shell, and the end head of the heat exchanger. Okay, so what are these TIMA R, TIMA C, and TIMA B? It's just a different type of processes that you will qualify your exchanger to be used for. TIMA R for, it has, it's usually for, very severe, or it has a lot of requirements, usually for oil and gas. And it has a lot of requirements that has to follow. TIMA B is similar to the TIMA R class, but it has less requirements, and it's usually for chemical processes. And TIMA C is also qualifies for chemical processes, but it has less requirements. So those are where you qualify. I think I press, here you have a little application when this TIMA classes apply, right? And normally, depends on what you qualify your process, you will select one of this. And we'll go through it, where you will select this different TIMA standards and TIMA classes. So what kind of equations do we use in the model, in the software? So CHEMCAD uses, when you select an exchanger on a flow sheet, we'll use this equation. And we all have learned this equation in university or when we went to school. The Q, or the enthalpy, or the duty of a heat exchanger is equal to mCp, the factor, but the temperature difference. Q will be the heat duty of the exchanger. M is the fluid flow going through the exchanger, and Cp is the heat, the fluid heat capacity or the specific heat. The temperature difference, the delta T that you see here, and F is the correction factor. This correction factor is the function based on the fluid temperature going in and out of the exchanger, and it's also a function of the number of tubes and shell passes on the heat exchanger. Okay, so it's not only based on the temperature difference, but also on the temperature on the shell passes on the heat exchanger. Okay, so that's, see, this equation is based only on the fluid flow. Okay, we're basing on the fluid going across this exchanger, and that is CHEMCAD. But what about CC term? CC term bases an equation based on another term, also on Q. Q, heat duty, will be U A LMTD. But then what is this equation? Well, U is the heat transfer coefficient. A is the area of this heat exchanger. And LMT is the log mean temperature difference. So it's the different calculation of the log mean based on the different temperature for what comes into the exchanger to what comes out. A is the area, or what number of tubes and shell is being occupied in here. So how many tubes we have. So it's the geometry of this heat exchanger. And U is the heat transfer coefficient. How did we calculate that? How do we get that number? Interesting. Well, that number can be estimated based on the process that you have. And we can have, we can get into, depending on the method or the process that you have, you can get an estimate of this. So depends on what you have. You can say, okay, well, I have an aqueous solution coming in, an aqueous solution coming out, and the other side. So it could be this value. So you can take a minimum and maximum, get an average, and you assume a value. But that is an estimate, and you can overestimate or underestimate the system. So how you do this better? Well, we can actually use CC term to rigorously calculate this value for us based on the information that we have on the fluids coming into the heat exchanger and the geometry of the exchanger. So what are the models that CC term uses to actually get all these values for us? How can it help us? Well, it offers us sizing, so we can have, based on the data that we have in our plant or the data that is given to us on our fluids and temperature and operation conditions, we can actually size a heat exchanger. So we can have an estimate of what the area can be, okay, of this. Or we can actually get a rating of, if we have an exchanger that exists in the plant, we can actually rate this heat exchanger and see whether this exchanger is actually doing the job that it was meant to do. Is it evaporating as it should? Is it condensing as it should? Or it's just not really doing what it's supposed to do? Okay, is it being efficient as it should be? Okay, is it taking 95% of it to just cool or warm the liquid and only 5% to condense or 5% to evaporate? If that is what has happened, this heat exchanger is not very efficient. So rating gives us that opportunity to see what is happening. So we get an existing heat exchanger and rate this, but also give us the opportunity to optimize a design. So if we got an design that we have, we have done our design, we can optimize this design and make it our own and make it to match the conditions or the design conditions we want. Okay? And that is what we are going to do today. Okay? And falling rating, it actually allows us to actually consider fall. Every process that we put through a heat exchanger will fall over time. And heat exchangers will need some cleaning depending on what is going through a heat exchanger. So this falling could be, it can vary from being very clean, which doubted that it will be all the time clean, to a severe or extreme condition. So it could vary from 0. We'll say 0.001 to 0.005. So you are in between. What value would you actually consider? And would you be overestimating this value or underestimating this value? How would you know? If you overestimate this value, you will be cleaning this heat exchanger too often. So cost of maintenance will go high. If you underestimate, then this heat exchanger will fall a lot. Then cleaning, it will not be cleaning, so it will not be efficient as it should. So you will not be getting, it will not be as efficient, right? So it'll be falling faster. Okay, so finding that correct falling factors or using something that is more efficient for your system is actually quite good. So it gives us the option to actually rigorously calculate this value and give us an estimate that is good or reasonable for our own system based on the data that we have. Okay, and we're going to do this. So next one. So let's go to our case study because this is what's important. This is our process, and there is some requirements on here and some constraints that we have to match. So we have the process. This is the whole plant, and they have told us that there is a exchanger required that is going to be added, and they tell us that this is the exchanger. The exchanger is going to be placed right here between these pipes. Okay? And it needs to be sized. There is a requirement not only for the size of the heat exchanger, but also not the size of the heat exchanger, but the length of the heat exchanger, but also for a limitation for the actual utility stream. Okay, so let's go see what this utility stream is. Okay, so let's go to our first case. So what do we know here? So we don't know the utility stream because there's a limitation. So we need to find out what the utility is. So what do I know out of this? So since I know the plant, I know this. I know the conditions that are coming into my heat exchanger. Okay, so knowing this, I can actually find all this. And that is the beauty of CHEMCAD NXT and CC term, that it will allow us to find all the answers that we want with just using this. And we're going to do that right now. So let's go back and get our hands into modeling this system. Okay, so let's go to our first case. So case sizing the heat exchanger. And this is the problem. So we have a process that requires an exchanger. There exist a few constraints that needs to be met. And the process flows needs to be cooled to 110 degrees Fahrenheit. That's the requirement. How big the exchanger needs to be and how much utility is needed. Those are the two questions I need to answer, pardon me. We have the process flow, which is, I just took a snapshot of that actually exchanger out of the flow sheet. So it's here. So we knew this here. This is our utility flow. So we know our process flow, and our process flow is a mixture of water, toluene, and nitrogen at these operating conditions. And the utility flow is water at these conditions, and there is a limitation. This limitation tells me that my water cannot be greater than 100 degrees. The outlet temperature of the water cannot be greater than 100 degrees. This is pretty much what this is telling me. The different temperature between the outlet and utility stream is 10 degrees Fahrenheit. Okay, so the constraints we need to match is that the tube length should be less than 8 feet long. The shell side pressure drop should be less than 5.5 psi, and the tube side velocity should be greater than 5 feet per second. So this is a little bit more of the heat exchanger. These are process and this is all related. So how we're gonna do this? Okay, so let's go to CC term. This will take us to CC term. So here is the process. So I model the plant. You don't need to have the whole plant, but if you have it, so if you have already a simulation and you can insert your heat exchanger here, we have our process here. It's already running, right? Now, I want to talk to you something that is very important. When we talk about modeling a case in heat exchangers or any case, it is very important to know not only the components that we're dealing with, the fluids that we're dealing with, but the thermal that we are using on the system. Okay, so I was told that I have water, toluene, and nitrogen, and I know that water and toluene forms two phases. So my thermal is very important. Also, the data that my components have is very important. So I need to know, so if I go to my home on the ribbon of CC term, I'm sure that all of you know already CC term, ChemCAD NXT interface. If you go to home, component database, view components, I can call in into any of my components and look at the data of my components. If I am going to size a heat exchanger, the very important data that I'm looking for is heat capacity, because I want to know what is the heat transfer between fluids. Okay, so heat capacity is very important. So I need to make sure that this data is there. If I am creating, for example, a new component, I need to make sure that I regress data for that component. So I will need to have that data in here. Okay, so that ChemCAD and CC10 will use that data to identify that component correctly. So in this case, it's correct because I am using ChemCAD system component databases. But if this will be a user-specified component, then I had to make sure that this data is there so that the component is identified properly. So I will do that with all the different components we have here. Yeah. So now the components are okay. The second step will be to see my thermophysical. So my thermophysical sometimes can cover, if you use the wizard, it will tell you that, it will select, because it's an algorithm, it will select whatever, based on the algorithm, it will select something that, say, oh, maybe vapor liquid equilibrium. But I know that water and toluene form two liquid phases. So, okay, I have NRTL. Yeah, NRTL is good because I know that ChemCAD has the BIPs, which is the binary interaction parameters for the system, which is in most case water and toluene, and it's going to perform vapor, liquid, liquid, solid, two liquid phase calculations. Okay, and if I say okay, it's going to give me the parameters for the system. And as you can see here, this system says liquid liquid equilibrium, but it is because I already chose it. You see, if I click on this little three dots here, it will open up what this system available BIPs, are. And in here, normally it will select this one, okay? But because I know that this system forms two phases, I will select liquid liquid equilibrium. So I say, okay, now my liquid liquid equilibrium is here. So now I have that option, okay? So now I not only have the correct data for my components, the correct data for my thermophysical, the correct model for my thermophysical, but now there's only one more thing I want to make sure, and it's my engineering units. So I want to make sure that my engineering units is correct. If I didn't model this system and somebody else did it, I need to make sure that the units I'm going to be using is correct, okay? Or the data that I'm comparing with is the same. So I am going to be using English units, which is what this model was using, and the data that it was being compared to. So if I was using something else, SI or any other type of units, I will actually check my engineering units. So I will go to, sorry, it just popped up in the wrong window and I'm trying to move it. There we go. So I will look into my engineering units and check the correct or change the correct parameter to the correct units that you're using. Okay, in this case, I'm just using the English units, which is the default one for ChemCAD. Once that is done, you are set to start modeling. So now you can just go ahead and move. So right now, the only thing I did, I just put the heat exchanger. So I said, well, the heat exchanger is going to go between these two. And the only thing I know, as per the example, was that the process had to be cool to 110 degrees Fahrenheit. So I entered that information there. There is no other information done. Okay. And then I knew that there has to be, this is going to be cooled by something. So I specify, some water is going to be used. I knew the conditions of the water, so I entered that specification. I don't know how much water. I just say, okay, that's the water. But I really don't know how much water. So I just run it. So this message here is because of this here. There is no, this pipe is not giving me, so I say there is no flow. And that's because there's no flow. So let's go avoid that. Okay, we're not going to look into that. So it doesn't have nothing to do with this particular modeling. So I just, give an estimate. So I have, some flow going in. But now let me look more into the problem. So I only said, that is going to be cool to 110. However, I do have more specifications. It told me that the difference between the inlet and outlet temperature of the cooling system was 10 degrees. So if I go in here, so what's my stream? This is a stream 19, as you can see in there, and this is a stream 20. So there is a restriction in here. So the stream between 20 and 19 should be 10. Yeah. Now I don't know what the stream should be, how much fluid I really need to cool this, to properly cool this fluid. So I really need to recalculate that because what I did was actually just enter a number, but I actually can recall. So now, as you can see, if I calculate flow of a stream, says enter two specifications, the flow of a stream 19 will recall. So now I have one specification and two specifications. Now it's going to recalculate the flow. You see here, I said it was only 100, right? Let me recalculate that. So if I go back, it recalculated to be about, what's my flow? 224 gallons per minute. See, I was underestimating the amount of water needed for this process. And this is just using the simple unit operation. We haven't even gone into the rigorous calculation. There is something else in here. I didn't take in consideration the pressure. And when we are doing a heat exchanger, we need to switch. So I can add actually a little bit more in here. Well, I can say that my process actually maybe, I can add some pressure, but I can let let me see, let me just do some specifications, maybe do 3, and I'm going to say 0.2, okay? And there's something else in here, I can add some pressure. Now, do you see in here that my correction factor is 1? It cannot be 1. It has to be more than that. It has to correct this endpoints. So if I have 1 pass on the shell and 2 passes on, minimum 2 passes on the tube side, what happens? I run it. You see, now I have sort of a correction factor. So that looks a little bit more decent to me. There is a correction factor. So I have a calculated heat use that is a little bit more. So I can go with this and now go into CC term. Okay, so now I can go with this and say, okay, that looks all right. I have this. I can go with CC term. So I now have an initial estimate that I can go and say, okay, I'm going to go into CC term and start modeling and sizing my heat exchanger. So I can select my heat exchanger. So everything that we have done it in CHEMCAD unit operation. Okay. So now I'm going to go and size my heat exchanger. So I can go to sizing. It's going to be a shell and tube heat exchanger, and it's going to ask me to put a name. So in here, I'm just going to say, I'm going to call it case one, since I'm just going to follow whatever is on the on the on the presentation. Okay. And now I created my case, and I'm going to go to general. In here, it's going to ask me where my tube side is. My tube side is going to be, I think it was 19. Yeah. My tube side is 19. Okay. And I can go in here and the CC term is going to pop up. Okay. Now, when this is when CC terms first dialog, it's going to tell me what is my team standard. Is it team R? So here is a team standard, is a team class or a standard. So from here we can select what kind of a standard we're going to follow or a team class. In this case, we're going to follow a team class. So we're going to select team R, team B. Okay, because it's a chemical reaction, it's just going to be team B. Okay, we're going to use this regular AEL, right? Nothing else in here. Nothing's going to change. There is modeling methods that we can change in here, but I'm just not gonna leave it. I'm gonna leave all of this. And we can go in detail on this, but it's gonna take us a long time, more than an hour that we have today. But we can go into more detail on what this means. But these models I use to calculate the heat transfer coefficients and all the different models that we use for the different types of models, like turbulent flow, laminar flow, two-phase flow, and all the different types that CHEMCAD uses for the different positions and processes that we see and detect when a model is being, when exchanger is being modeled. Okay, so that is being done in here. I say okay, and as you see, it's just considering that this is a clean process. Okay, then on the same icon, which is the general icon, I'm gonna click on the little arrow down, and I'm going to go to the design constraints. The design constraints are going to appear, and I am going to model this design doing everything. So it's going to size the nozzles, and I'm going to use the design criteria that we have in here. But I'm going to give myself about a 10%, override, meaning that if by any chance there is an increase in flow rate or something, there is a 10% override on this design. Okay, that gives me an option to just actually, play with it while I'm optimizing the heat exchanger. Okay, this, some people uses 20, 15, 5%. It's just your criteria. I use that. So it's not something you have to follow. Some people just chooses not to select this, but it's up to you. It's your criteria whether you want to follow that or not. I like to optimize the number of tubes so that CC term can follow the best option, how many tubes are being positioned within the shell. Okay, so I'm not going to change the design criteria. As you can see, CC term uses to size regular industrial heat exchangers. Okay, so I say okay, and now we have our design criteria. Sometimes we have design criteria depending of the objective, right? Sometimes we want, different, so then we can change the design criteria. But in this case, we don't. I don't have a design criteria change, so I'm just leaving it as the default, right? So now I can see, I can now just see, if I want to at this moment, I can see my chart. I can see how my heat curve looks like. You see, yeah, it's all right. It looks all right. So now I go back to my model, and I can just see the geometry of the heat exchanger. I can go into the tubes, and I can see that there is many values in here that I didn't enter. Yes. Why there is this values in here? Well, there is values in here because ChemCAD CC needs some defaults to calculate preferred calculations. Otherwise, you will have to enter this value. So we have some entries already based on what TEMA has recommended or the handbooks of heat exchanger design has recommended to be there. So these values are in there. But there is options. You can actually enter, like the number of passes, for example, number of tube passes. But you see those asterisks that you see besides the field? Those are the values that the CC term is going to recalculate for you. Okay, so in this case, the number of tubes and the number of tube passes are going to be recalculated, or they're going to be designed for you. Okay, what we can change is the tube, the tube outer diameter, the tube wall thickness, the tube length is going to be calculated or designed, but the rough factor, the tube pattern here, we can change it to 30, 60 of the rotating ones, but we want to accommodate as many tubes as we want. So the 30 in triangular 60 will be the best option. 30 will be the best option in this case, the cheaper and the more economical. Tube pitch, we're going to leave the default in here for now, and the other options as well. Okay, so we go. Or shell is the same thing. It's going to be recalculated. And baffles. These are going to also be calculated by the software. Okay, all of them. And the nozzles as well, as you can see. Yeah? So that's all what I need to do. Now what do? I go to the run. So next one, we have gone through here, geometry. Now we go to the run calculation. We drop down the arrow, we select from the run and go design. As you can see, it quickly has run the design criteria or the design calculation. And now we can go to our results and we can run or view or report. The first report that pops up was the optimization of the design. And it took 13 runs to find this particular design. Okay, this is the last calculation. And this is the values based on all this that are now on our design. So, and if we go, I'm not going to save this. And if we go through that report, you'll see. So let's go point out what we see in here. So this is our summary. So on our summary, we can see that our tube length was calculated to be 8 feet long. Okay, not so good. Our shell side pressure drop was calculated to be 2.7 psi. Not so good. And my tube side velocity, okay, we have something good here. Only the tube side velocity. Okay, and okay, it's about effective air, it's about this. Okay, well, that's all right. But first of all, our tube length is 8 feet. We have to be less than 8 feet. Okay, this is barely going to fit to the constrictions that we were given. Okay, and our tube side pressure drop is way high. We're supposed to be less than 0.5 psi. So the only thing we're good here is this. That's it. And barely too, barely, because it's supposed to be higher than 0.5. So we have to, this was our design. So CC term it tends to design a heat exchanger that is low and economical, right? So that's a cost analysis at the same time. So we be a loan and economic heat exchanger. But sometimes this will not fit what our criteria is. So we have to, now we have a design, but we need to optimize it. And that's where our second case comes, when we have to optimize this design to fit the criteria for our process, all right? So now we can close this case, okay? So now we can go back and said, okay, well, this is my case. Let's go back and so let's go do my second case. So look how easy it is to create a case in CC Term. So I did my design case. So let's go, you see this little, in the select options, you have different options here. And you can say, okay, I like what I see in here. However, I want to do some changes. So I'm going to copy this case. So you see this option, you can go here. I'm going to copy this case and I'm going to rename it. So that's case number 2. Okay. Now I have my case number 2. Okay. But what are we going to do in case number 2? So let's go back to our presentation. So we did our sizing. So as you can see, the values that you see in this report might change a little bit from what we're doing, but as we can see, everything is sort of the same. Like it was a little bit too big, the shell pressure drop was too high, and the tube velocity was a little bit greater than 5 feet, but we can even maybe increase it a little bit more. Okay, so what we need to reduce, what we need to do, we need to reduce the exchanger tube length, and we need to reduce the shell side pressure drop and increase the tube velocity if it's possible. All right. So we need to do that. All right. So now we're going to do our case 2. So we're going to rate the heat exchanger. Okay. So how are we going to do that? We're going to increase the shell diameter to accommodate shorter tubes because we are going to reduce the length span of the heat exchanger. That means if you're reducing the length span, you're increasing the shell diameter, okay? And we're going to do one step at a time. We are going to increase the tube side passes from 1 to 2 to increase the tube velocity. Our tube velocity was a little bit high, like from what the specs were, but we can increase it a little bit more. So we're going to increase it from 1 to 2 and see what happens. And we're going to change our baffle from segmental to double segmental. And we're going to increase the baffle cut from 20 to 25. I'm not, I think, no, I don't know what it did. I didn't check the baffle cut, but we're gonna check that. Let me see what it was. Okay, so we're gonna do that. So let's go to, I forgot what it was on that case, but let me just check. I don't remember what it was in that report, but I'm not going to generate the report again. So let me just go back to what we're doing there. Okay, so let's go and do it anyways. So we are now on this case. So let's go back and we are going to go to our shell first. So let's go to our shell. So we're going to increase this shell. So we'll say we're going to increase it to 10. So we're going to increase the shell size to 10 inches. If we do the calculate tube count, it's going to tell us how many tubes is going to fit in this particular shell. Okay, so it says that it's going to fit 77. Okay, 77 tubes. So we can go to the tube here and say, okay, it's going to be 77. Okay, there's going to be, okay, I'm going to put maybe 74 or maybe, yeah, 74. And I'm going to increase the number tube passes to 2. Okay. Where was my, okay, that was good. And I'm changing the tube length to 6. That is a good size. Okay, now let's go to our baffle cut. That's what I wanted to go. This is going to go to double segment. Okay, you see how many, this is why the pressure was too high. It had 31 baffles. That's a little bit too high. So I'm just going to reduce it to maybe 9. Okay, and this is 17. I'm going to put maybe 20. Okay, we're just going to see what happens here. Okay. Another thing to note is that CHEMCAD has in here in the baffles, we have a spacing definition of edge to edge. TMA usually does center to center when it reports on the TMA spec. So you can either do one or the other, right? So it's just in the specification, but the rest continues the same, okay? So if we do that, so we increase the shell diameter, so we have a shorter tube length span. We change the tube length. We change the tube, this has been done. We change the tube, the number of tubes, the tube length, and the baffle. So now we can go to our run, okay? And we can say, let's go rate this case, okay? So now we're not doing design, we're doing rating because we want to see what the performance of this heat exchanger is, okay? So we run the case, and now, okay, CHEMCAD CC-term has actually done the rate. So we go here and, okay, so let's see what happens here. Okay. So we see that our excess has increased a little bit more, but it's okay. We don't worry about that right now. We're just still analyzing. Our shell pressure has dropped considerably, as you can see here, 2.4. So we're below what we wanted to see. You should be less than 0.5 psi. Our tube velocity have increased quite a bit now to 6.4, 6.5 feet per second. And of course, because we reduced the tube span, now we have 6 point length, okay? So we'll worry about this. So far, our affected area is this much, and we are a little bit, but if I were to increase the amount of flow going, then that will be within limits, okay? So it depends. So what if I change a little bit more? Okay, so we are okay. But what if we do a little bit more of change? Okay, so what if I move this a little bit more? Okay, so let's go do some more changes. Okay, so this is good. But as you can see, we have dropped considerably the amount of information, the values a lot. So let's go to our presentation. And we did our case, and we have dropped the values that we calculated before quite a bit. But we also, I forgot to mention that through the report, there was a decrease in the amount of the heat transfer coefficient. And that's because of the changes we made, okay? So every time that we do a change on the heat exchanger is a give and take. So we had to see how a change affects all the variables in the process or in the modeling that you're doing for the heat exchanger. Okay, and because our heat exchanger or heat transfer coefficient decrease, of course, the overall heat transfer coefficient also decrease a bit. Okay, so what we can do, we can actually we can try a little bit more. I mean, if you want, you can drop the pressure drop even a little bit even further by trying different shell size. But let's see if we can try something else. We can actually try changing, increasing the shell a little bit more. Okay, we can try to do that. Let's go try another case. Okay, so we can change the diameter a little to accommodate more tubes, or you can even increase to maintain the tube velocity. You can just keep increase the tube pitch. Okay, and make sure, because if you notice, there was a vibration flag on the rating case. So we had to see that too. So let's go see this case a little bit further. So let's go to CC term. Okay, so this case was okay. So I'm just gonna modify this case. So I'm gonna do another case. Okay, so now I am gonna modify this by just I'm going to change the tube pitch to 125, okay? And I'm going to increase the shell to 30. So this tells me that I have 74. Okay, so but I already have 74 tubes in here. Didn't I? Yeah, so I had 74 tubes. Okay, so I have 74 tubes. I did my, okay, that is good one. And I did that. Sure. Yeah, that's good. 5 bubbles. Good. Okay, so this is, okay, what does it say? Okay, the baffle center spacing. See, there is a warning in here. And that is because we are following TMA standards. Now it tells me that it's minimum 2.6. Okay, so the center spacing, because I changed, the center spacing is not, this center spacing is too small. So it's just, so I'm just gonna clear it just because it seems that this was specified. So I'm just gonna clear it. Let me see if I go to center. Oh yeah, let me buy if it's gonna clear it when I go. Yeah, it's supposed to be 6. So it's just gonna divide it. It's just way too a little bit. It was not making sense to what it was. So it just clears the back. I usually work with center spacing, center to center, because it's easier for me to calculate it instead of taking into consideration the width of of the the baffle. So it's just that was a warning because of the specification that it was giving here and because of the changes I was making. It just didn't like this spec. So this is following TMA standards. This is your specs, but CC10 will always follow TMA specs when it regards to baffles. Okay, it will always tell you whether there is a warning, so you need to change it, or whether it is feasible to put those values into the exchanger, right? So now we did the changes. Let's go back and rate again this case. And it did run. Okay, that was fast. Yep, okay, so then let's go see our report. So, and as we can see, oh, look at that. Now, and this is what I wanted, that's what I was looking for. So now, as you can see, I expanded. What I did was open it up, the tube bundle, okay? When I did enter the pitch, I increased the pitch from 0.9 to 1.25. I opened up the tube bundle, right? And what happened here is that when I did, not only did I keep the limitations that we have, and we still okay, but look what happens. You see, I am beyond, like I said, the actually required by the fluids is 85%, 85 feet square, while the effective area is 84, right? 84.6, 85.3, which put us to be in excess of minus 77, which means we need to work a little bit more on this. So you want to be even right on 0 or above, but not below, because then you will have an exchanger that is undersized and it won't be able to do the job that you're looking for. All right. And that's what I wanted. Like, of course, when you go out there, you won't have, it's just it's an inefficient heat exchanger that is not sized properly for the job that it was meant to be to do. Okay. So what we need to do is just change the parameters that we were doing. Okay, so we can go back, and this is the beauty of this. You can go back to the previous case you have, or you can change this one and rerun the case. So if you actually like your previous case, you can go back to that one and redo that one, or redo this one, delete this one, and you just redo the things, or just go back and change the specs that you have in here. Okay, so in this one, what I'm going to do is just increase. I can increase actually the shell diameter, maybe put 3.5 and 80, and I'm gonna put 80. And run. Okay, so here we go. So what I did is just increase the shell diameter to fix this. So 6, this is my tube length. I'm within the criteria. My shell side pressure drop is still within the criteria. My tube velocity went a little bit lower, but it's okay. It's because, but I change it, I can increase. It's just because I increase more tubes. But as you can see this, I can actually put 0.25 and my velocity will increase as well. So we can actually do that. There is no flags, so let's go back here. Perfect. So we have everything now. We have everything. Our fill coefficient is okay. Cool. So we have, there's no flags. Everything is good. We're still within the criteria that we have been asked. And as you can see, our velocity is up to 6.2. Okay. So this is good. Okay. So we have now something, but now we have our case. But what if we haven't taken into consideration even falling factors? So we need to do that. So what is falling factors? So we had taken consideration the fall based on the fluid that is going across the heat exchanger. So we can do that. So we can save our case, and we're going to change that to falling factors. How do we do falling factors? So I'm sorry, I'm ahead of my. So case, I'm sorry, go back to our case. Sorry, I'm ahead of so our cases, as we can see, it was okay on our last rating. We did all right. Everything was okay within the limitation. We were above, and it was good. And we have an area of about I think it was 80, about 80%. But we are not finished. We still have to take in consideration falling factors. So let's go see our falling factor. How we do falling factors, and we're going to go through to do this into CHEMCAD. And we can take in consideration falling factors for the shell and falling factors for the tube side, or even both. And in this case, we're going to do them for both. So let's go back to CC term. And if we go, we have copy already or case, and we go to here, and you see on our general specifications, you have an option for falling factor rating. And this would allow us to take in consideration fall, to estimate fall for both sides. Say, okay. And we go into the run. That's the only thing you have to do. And on our run, we select falling factors, and it runs. Okay. Now, if we go back into our general specification, you'll see that the software has calculated this for both. And you can see this in the report. So if I go back and see on the report, this has been calculated for both factors here. Okay, so now we have falling factors taking into consideration for our system for the process. Okay, so now let's go back to our presentation. So we have now taken into consideration falling factors for both of them. Now the process or the exchanger has been rigorously calculated, size, rate, and now we take in consideration falling factor. Now we're going to move into integrating the exchanger that we have into our simulation. Okay, how we do that? That's what we call simulation mode. And simulation mode is an option that allows it's a simulation that rates directly the exchanger from the simulation flow sheet. It takes the heat exchanger duty, outlet temperature and pressure drops, and calculates the exchanger based on the geometry that has been sized. Okay? And it does this over and over. When you do sizing, rating, and falling factor, the CC term takes into consideration the heat curve once. But when you do simulation mode on CC term and CHEMCAD together, the heat curve for the exchanger is calculated multiple times. every time, is calculated every time the simulation runs. So the heat curve is calculated for every iteration that heat exchanger is run. Okay, so how you identify the case that you're happy with within CCTerm, and you selected a simulation mode. Okay, so let's go do that. So here we go back to our simulation here. So in this case, I am going to select, so I'm going to copy that, and my case will be number 5. And now, when we do simulation is always a rating case, okay? So this, case 5, will be my simulation mode. So I'm going to identify my case as simulation, but look what happens when we identify a heat exchanger as a simulation mode. This scene is going to completely change, okay? Your screen on the heat exchanger dialog is going to change. So this is my case, and I'm going to identify it as a simulation mode. Here we go. It says simulation. It's going to tell you, is this what you want? Yes, I want that. And now it is. This is my simulation mode. And now it is done. I can save my simulation. It's done. Look at it. This have changed. It's not calculated yet, but look what happens when, yes, it tells you it's case 5 that you chose as your simulation mode. I can go home, use the run simple mode in CHEMCAD, and run the case. Did you see? That is the heat exchanger. This is the heat curve that was run for that heat exchanger when the simulation was run. Now, if I go back to the exchanger, I can see that the heat exchanger was calculated properly. This is my heat transfer coefficient, my area, which it was about 80, something 90. The pressure drop calculated. And if I go back to the calculated, this is all the difference. The tubes are falling, all the data that was calculated in CCTerm. So now I have sized the heat exchanger. I required about an 88 feet square heat exchanger with a utility of approximately 224 gallons per minute. And I have optimized this heat exchanger in about an hour, I think. So here is what we have gone through. It's about, well, the values are a little bit less because, I took a different specifications, but it's approximately very close. And as I show you, CCTerm will display the calculated values and the heat curves that is run every single time, right? And with this and in review, we have explained how CCTerm can be used to design a new heat exchanger and demonstrated how to rate an actual exchanger to evaluate and optimize the exchanger performance, and demonstrated how to use CCTerm options to integrate the exchanger within the process model to perform rigorous heat transfer calculations. And with this, I would like to thank you for your time and your participation. If you have any questions, thank you for your time. And with this, if you have any questions, I would like to take them now. Thank you.